This lesson, as you can see from the top bar on the webpage, is called First Past the Post, and it's got a very obscure picture of horses racing, and I'm going to explain all that as we go through this video. So the main idea behind this lesson is proportional thinking or proportionality. Okay, now when I took a look through the curriculum, I didn't find that many expectations that related specifically to proportional relationships or proportional thinking. But it turns out that it's really present in most, if not all, of the math that we teach. It's a very important, big idea. The curriculum that we're currently working with in Ontario is quite old, from 2005, and we know, most of us know, that recently proportional reasoning has come to the fore as a very important part of mathematics throughout the curriculum, throughout all grades, and throughout all strands. And the new monograph in 2012 describes in great detail how important proportional thinking is from K to 12 and across all areas of mathematics. So that's what this lesson is going to work on. The problem with proportional reasoning is that it's often taught in a way that's not effective. And let's just take a look at an example of a question. So here is a grade 8 expectation, a specific expectation. Solve problems involving proportions using concrete materials, drawings, and variables. That's a great expectation. My problem is the sample that is given. The sample problem. The ratio of stone to sand in hard fast concrete is 2 to 3. How much stone is needed if 15 bags of sand are used? Now, I can explain to you why I think that this is not a great problem, but Dan Meyer does it better, so we're going to watch him talk about engagement in mathematics. Listen.
Will not be interesting. It's a really strict biconditional relationship. And I'm looking at counterexamples of that right here. These problems fail to light kids up. And I think I know why. We're here in the San Francisco Bay Area. This is my homeland here, and I've actually, we have whales that pop out of the water nearby, and I've been there with friends of mine on the rocky bluffs, watching a whale pop out of the water. And I can tell you that I've never once said to a friend while there, hey, are those triangles out there? Are they congruent? Could we prove it? And so, and this is serious, this is real. Like if I, as the most enthusiastic mathematical member of my social crowd, if I would never draw that connection, what does it do to students when we impose that connection on that poor whale? Does math grow more real, quote unquote, or more alien and abstract, foreign and odd? I think the latter. I was even, I was on in Alaska with a group of math and science teachers on a boat on a whale watching tour. It was like you collect everyone in Alaska who loves math and science, and a large portion of them were on this boat, no one else. And we saw this whale pop out of the water. Do you know, can you guess, estimate how many of the teachers on that boat pointed out the congruent triangle? Do you know? Hold up a number of fingers. No one's going to guess here. Saying zero. In fact, it wasn't zero. It wasn't zero. Congruent triangle. Huh? That was me. That was my voice. I said that. You said zero, you were wrong. It was one. The answer was one. Oh, yeah. Will not be.
So Dan Meyer's point is well taken, that sometimes the problems that we give for proportionality or for math in general just aren't engaging to the students. I don't think many students really care about the triangles on the whale's flukes, and I don't think many students care so much about the ratio of stone to sand, because it's not really connected to them. It's not important to them. Here's another question that could be used to teach proportionality. A snail can move I inches in m minutes. At this rate, how many feet can it move in h hours? And again, I think Dan Meyer would weigh in here and say that, I don't think anybody's ever really considered when they've watched the snail, like, ooh, I wonder how fast or how many feet it could move in an hour or 2 hours. I just don't think that happens. Now, I chose this snail question specifically because years ago I was driving to work, in the morning, listening to the CBC as I often do, and there was an interview happening, and the fellow who was being interviewed was this guy right here, David Stocker, and he was talking about this book which he wrote, which was new at the time, Math That Matters, and it really sort of changed the way that I thought about teaching mathematics. This resource contains lessons that use mathematics as as a tool to examine social justice issues. And the one we're going to be looking at today, well, my lesson is based upon lesson 37, The Winner Takes It All, which examines Canada's electoral system, which is called a single member plurality system, or more commonly known as first past the post. Which brings me back to the picture at the beginning of of the of the video. First past the post is a reference to a horse race that the first horse past the post wins everything, and there's no second, third, fourth, or fifth place. There's nothing for them, and that's very much how Canada's electoral system runs. Within each riding, the first person past the post, i.e., the candidate with the most votes, gets the seat in the House, and all the candidates get next to nothing. So, in this lesson, David Stocker highlights the fact that in our current system, the number of seats that a party wins is disproportionate to its share of the vote. And we're going to see some examples in just a minute about that. And he suggests proportional representation as a fairer system. So this is where the math comes in, the proportionality. The number of seats a party gets is proportionate to its share of the vote. So students, when they're looking at these different systems, get a view of how one system that is where we have more proportionality existing and working, and the current system where usually the results are not proportionate to each other. Now, I know what some of you are thinking, that you're thinking, okay, well, this is about increasing engagement in mathematics, and you're giving them Canadian politics to do it. Are you crazy? But I've done this before. I've taught this lesson before, not with the coding aspect to it, but with the electoral aspect to it. And it does get a lot of engagement, and basically through outrage. Okay, because once students have an innate sense, young people have an innate sense of right and wrong and what is fair and what isn't, and right or wrong, a lot of them take immediate issue with the fact that a party might get a certain percent of the vote and get a number of seats that doesn't represent that. And let's take a look at an example. Okay, so in the lesson below, students are going to encounter, first of all, this image. And this is an image of results of the most recent election in Ontario. Okay, and as we can see here, the Progressive Conservatives received 40.5 or 40.49% of the popular vote. And they won well over half the seats. They won 76 seats. Now, 76 of the 124 seats, that's 61.3%. And this is where students get really, really concerned and engaged with this, because they right or wrong, they say that's not fair. If they got 40.5% of the vote, they should have 40.5% of the seats. And they recognize that if their percentage of the seats is higher than their percentage of the popular vote, they recognize that some other party is getting a percentage of the seats that is less than the popular vote. Okay? By comparison, the Liberals received almost 20% of the popular vote, but look at the number of seats and the percentage of seats. They won 7 seats, and that translates into 5.6% of the seats. And this is where students will look and say, that's not fair. And as soon as they've said that, then they're engaged. They want to do something. They want to change it. Now, I'm not saying, and I don't weigh in and try to persuade them that proportional representation is better. I say these are two different systems, and I let them decide. Neither system is perfect, but from the outset, the general first reaction is first past the post isn't fair. And then as we go and learn about the different aspects of the two systems, then students are able to make more educated opinions about them. So, in first past the post, the number of seats is not proportionate to the share of the vote, and that doesn't make it a bad system. It just means that the number of seats is not proportionate to the share of the votes. Under proportional representation, a party's share of the seats in the House would be the same as its share of the popular vote. So, the PCs, by virtue of getting 45% of the popular vote, would get 40.5% of the seats, and that translates into 50 seats under proportional representation. Now, this will have a big effect province-wide on everyone, including the students in the class, because in that particular case, it would mean that the Conservatives' majority government would turn into a minority government, and that changes the landscape for everyone in Ontario. So I've done this lesson before, minus the coding, and using the students' innate sense of fairness, of right and wrong, to draw them in to be engaged in it works pretty much every time. Because this is closer to home, it's closer to their sense of right and wrong, and they're old enough to know that political decisions actually do have an impact on them as they learn about different issues, unlike, say, the speed of a snail crossing the road or the amount of sand in concrete. So, this is very similar to what Dan Meyer talks about in the same video later on about starting a fight, introducing controversy into the classroom. There's no controversy around some of these other questions, but there is controversy involved in electoral systems. So that is where we're going with the mathematics in this lesson.